I have a feeling that there was a whole quality that Conrad strove for in achieving what he termed a simple shell, that this was a kind of vacuum, that life would fill this vacuum. This would be its greatest adornment. Conrad stated it as integrity, honesty, humility, love and knowledge should be the ingredients of the use of these spaces. Conrad had a number of images of the future. And to speak of Conrad's image of the future, one has to speak of Conrad's courage to face the future. René Dubos' quote describes Conrad, quote, to have taken risks and have the courage to say no to things that have paralyzed one's freedom, and that the enjoyment of life has depended on taking risks, accepting the fight, and refusing comfort. Conrad was an incredible survivor, but always a survivor with integrity and principles unsullied. Conrad never hesitated to take the risks of imagining or projecting his vision in a form which so often achieved a remarkable symbolic quality which far transcended its visionary content. The great line fantasy, which Crombie showed, an exercise with a woven modular structural element, was an endless graphic maze, a labyrinth of visual delight. The motion machine became an offering to the image of the moving point in space of this whole rotational aspect of geometry that pervaded much of Conrad's images. The visual imagery of the interlacing networks of communication in his ideal comprehensive multidisciplinary scheme for building educational institutions conveys in a graphic sense what he intended in an organizational sense, although the strict organization is a hard one to imagine through the specific graphics, but the whole feeling of this was something that was eminently successful. In the book he was working on over the past several years, he saw himself as a joining link of this bridge in time between the past of the 19th century, still permeating so much of the 20th, and the future he is constantly anticipating and trying to accelerate. The present, a fascinating moment in passing between these two situations in history, where seemingly everything is possible, impose great obligations to anticipate the future. His yearning for the future reinforced his appetite for the humanity and the passing point of the present, a constant theme, quoting Conrad. And whatever does happen in this aimless, restless urge for change for tomorrow, this is the secret of my longings. Again, at this historic turning point, out of a kind of blank spot in between, a new stage set behind the rising curtains of the world theater emerges. It may be this particular situation which makes me look with envy into the future, so promising for the betterment of mankind. Change to Conrad was something you had to constantly anticipate, be aware of, be prepared to find, particularly in just the places you least expect to find it, and to welcome change when you find it in whatever form. He was fascinated by the forms of change which had taken place and were taking place. He was intrigued by the light bulb, that it had come upon the world with startling rapidity, from invention to working system within the years, and made greater impact on the environment than any building had. He was intrigued that the propeller had come and gone in flames, as the open flame had gone to houses and come back, that the wheel might go in high-speed vehicles. He was intrigued with the problem of transport and the modular revolution that had swept the shipping industry. He had designed overseas containers in the 20s from elements of the Christoph and unlocked housing units, which were then reused as housing elements on arrival. He was intrigued that everything now was the world standard in these transport units, that all the utilities were modular, with refrigeration units and electrical units, that the forms of ships and the bases of all the harbors in the world were completely changed. He anticipated that the whole mess of wires would go, as he put it. And the fact that restructuring of the whole satellite, the whole communication system in places like Indonesia are now by satellite because the wires are that much more expensive and involved as a system to install. And Conrad hoped to live to see some of the elements of this. I had sent some things to Conrad a year or so ago, and the fact that this was module on a module, bringing up to something the size of 5 to 10 kilometers. Conrad was fascinated equally with the whole future world of new forms, linkages and connections, and impact in the world of computers. It is interesting to look at the area of computer system design, that area called computer architecture, and compare some changing concepts with Conrad's, some of the parallels with Conrad's principles. These are, I won't, there are some intriguing parallels of the whole idea of conceptual integrity, uniformity, consistency, and regularity, the whole concept of orthogonality, which is really the independence of elements, but it is the objective of holding the number of basic concepts to a reasonable minimum, maximizing the independence among the concepts and avoiding superfluities. Much of this relating to redundant structure, and an architecture with a high orthogonality tends to provide more functions at a given level of complexity or cost. This, to a degree, is basic computer design over to simpler structures on the same function level. Conrad was intrigued with the idea that something as wondrous and previously completely mystical, like the genetic codes of the living cell, could turn out to be in geometric form of the DNA, built up of a double helix and a very limited number of imitating modules, incredibly long, but utilizing only those basic modules involved in himself. Again, a significant shift by the side to the side of simpler structure for complex function. There are parallels in some of the work even going on in the brain area where even this seems to be working over towards recognizing a simpler structure and in a direction where the whole quest for simplicity, something which Conrad understood at so many levels, this value of simplicity, the value of clarity, above all, it was his, above to Conrad, is this value in simplicity of approach to life, to people. Could it be that Conrad's long quest for simpler and more highly ordered structures to achieve given functional complexity reflects some universal principles we should not ignore? For myself, I will continue to keep in the area of this chart reserved for singularly elegant and effective solutions those references representing Conrad's images and the Japanese house. As a last comment, appropriately for Conrad, whose life was a series of coincidences, I will show you the cover of the book from which I made the slides of this Japanese house. I had noticed what I will show you for years when I first got the book, and I had intended to mention it to Conrad. I never did. He was never aware of it either. The book is a forward by Gropius, great emphasis on so much that was related to Conrad, and yet it never once mentioned the name Conrad Buckminster. And yet, the cover of that book has the hanger related to it. I felt the last few pages of Aspecta, some of the photographs of Conrad's marvelous book of photographs taken in Italy in the 30s would be appropriate. After that, there are 3 images Conrad made at the request of an old friend just a few days before he died. These and a letter were the last things on his desk.
Bruce Hamilton, it's yours.
Okay. As far as the note-taking goes, I don't... Tony suggests you take notes. I'm not sure it's that important because I don't have notes. It's not a prepared lecture. I've never given a lecture on this subject before. And what I want to do mainly is give you a feeling for what Fuller has done in terms of geometry. And the main reason I'm here is that I am from the real world, as opposed to what some of us in the factory refer to academia as the unreal world. And I know a lot of the problems that designers face with the factory, the marketplace, and I want to try to start from the concept and go to this product, which we are going to make, a big ball. This is a very small ball compared to the one we're going to make. But before we do all that, I want to sort of lay just the kernel in your mind of what the new geometry is about. This is the book that Fuller worked on. This book for about 50 years or something, I don't know. He discovered a lot of this stuff a long time ago, at least in very broad general outlines. The details of it he's been filling in since the mid-40s, and did a lot of it in the 50s.
Do you know any somebody who carries that book?
No, I don't know where to get the book right at the moment, but
It's in the SCI-Arc library. It's
Macmillan. Macmillan's a publishing company. Okay, where I like to start is, what is a bubble? What is a bubble seems to me to be the fundamental question. Every time the surf crashes, you see a million bubbles. The universe, on our planet, we must generate 10 gadzillion bubbles every second. All the kids blow bubbles. We've all blown bubbles, and you know that there's no thing there. You know, there's a soap film held in a circle, and then the breath goes in, and then very briefly there's a bubble. And all my tents, all the structures that we make or we see are just bubbles. Some of them have a longer duration than others, that's all. This is going to be gone this afternoon, equally as every bubble in the surf is only there for a second or so. And every one of those is spherical. It's a joke I like to say, did you ever see a cubical bubble? And the other guy says, don't be such a square. And there's really something about the right angle that is a basic misconcept. And that's what I want to try to get across to you. The starting place for what is a bubble is to look at these little things, these little toys that I make. And I want you all to feel these and pass them around. That's why I have them here. Clearly, is not a continuous surface. There are clearly a lot of holes in this surface. Just as in a bubble, the surface is not continuous, or in a balloon or a ball. Now, there are rubber molecules here, and there are interconnections between those molecules, and there are also spaces. If you were to put this, if you want to cut a section of this out and put it under a microscope, you could clearly see it's not a continuous surface. It just happens that the spaces, the gaps between the molecules, which on this scale, I can easily put my finger through and whatever. On this scale, they are smaller than the air molecules, and therefore the air stays in. Now, the question is, when you make a bubble, what's the air doing? Or if it's a balloon is even easier to conceptualize. It's very stretchy. There's no compression there. There's nothing there resisting implosion or dimpling or flattening. See, these will flatten very easily. So inside the bubble or the balloon, it's the air itself that acts as the compression that keeps it from squishing. Geodesics is simply a matter of taking the air molecules and arranging them in the most economical, efficient pathway and replacing the air molecules with some kind of a compression member or other. Now, what we have here are strips of mylar, and if you want to, let's pass this around the room. the difference in texture between one like this, which is clearly a bubble. This has a very definite texture of a bubble. This has the texture of a ball. This is almost a balloon. This is somewhere in between. The only difference between them is the compression members, the stiffness or the resistance to implosion of the compression members. Now, what does all this have to do with geometry? We've got to go back to the original geometers, the Greeks, and say, what are the tools of geometry? What do you need if you want to be a geometer? And there are only three basic tools. One is a pair of dividers. You have to be able to make measurements, and this is how you measure. And the other is a straight edge. You have to be able to draw. It doesn't have to be a triangle, but you got to have a straight edge. And the third tool is some kind of means of inscribing. You have to be able to make your lines once you've measured and you have your straight edge. And that was one of the basic rules that the Greeks had. You had to work with these three elements, and anything you constructed, whether it was a triangle, had to be done with these tools. And there is a fourth tool which was not defined by the Greeks, which Fuller defined, and that is the surface upon which you write. Because if we look at the surface of the Earth being as big as it is, and you scratch a triangle on it, if I were to scratch a triangle on the floor here, I don't consider that I'm on a surface of a sphere, and I don't account for the rest of the sphere. Because it is so big, it appears flat and it appears endless. Now, if I were to take my triangle and inscribe it on this coordinate system here, which is an XYZ coordinate system. Okay, what is a coordinate system? The basic structures, the tet, for instance, and the octahedron, which we have here, and the icosahedron, these were defined by Plato quite a while back. These are well known, but it wasn't until Descartes, which is just a brief second ago in history, that we had a means of saying, well, the tetrahedron, it's over here. I could say it's over here at -4, -2, in 6. That's where the tetrahedron is. Octahedron, it's over here, +3, +2, +6, whatever. So this is a system of relating objects in space to each other. Not just defining the object, not just saying that 4 triangles makes a tetrahedron, but saying this tetrahedron, I can locate it relative to what? Relative to this point, 0, 0, 0, relative to this origin. Now, the problem with this coordinate system is that these axes, as they go out, are all said to go to infinity. Okay, if those are getting distracting, we can just throw them out of the way, because I don't want to spend too much time on the ball, it's just there. Okay, so now if I draw a triangle on this, and I say a triangle is an area bounded by 3 lines. Okay, what does that tell me about all the rest of this coordinate system? Nothing, absolutely nothing. All I know is about what's inside these lines. If, however, I were to pick instead a different type of blackboard, such as this one, which is a blackboard, that is a whiteboard. It's the first whiteboard. Now, if I want to draw a triangle on this, and I say a triangle is an area bounded by 3 lines, well, this area outside those 3 lines is also a triangle. It's bounded by 3 lines, equally as the area inside that is. Now, if I take the most radical case and draw the triangle right around the equator, which I'm going to have a hard time doing, but it becomes very obvious that the three lines equally define both halves of the sphere. Not only that, but a sphere has an inside and an outside, and they are not the same. If I take a right-handed glove and turn it inside out and put it on my left hand, it's not the same as a left-handed glove. If it's a fur-lined glove, instead of having the leather on the outside, I'll have fur on the outside. Well, a spherical surface is always convex if you view it from the outside, and it's always concave if you view it from the inside. And a concave triangle is not the same as a convex triangle. For instance, if I were to hinge this triangle along this line and fold it back, if I make so that it's going to come over here, these two triangles will not line up, because the one will have this configuration and the other one will have this. Okay, the point is, working with the Descartes coordinate system, which has gotten us a long way, it gets you all the way to relativity, it gets you up to Fuller. You can't have Fuller before Einstein, you can't have Einstein before Descartes, you can't have Descartes before Plato and all that. But working with this system, there's a total bias towards what's inside the line and a total absence of consideration of the rest of the universe. Working with Fuller's geometry, anytime you define anything, you also define what's left over, the rest of it. You can't define one triangle without defining four. There's no such thing as one triangle in Fuller's geometry. Now, it's important. There are a lot of reasons why it's important. If I take this on a personal basis and I say to myself, what am I going to do? And my way of defining things is based on this type of thinking, then I'm very likely to say, well, I don't care what's out there on the X or the Y coordinate or anywhere else. All I care about is what's inside these lines, me. Whereas if you're working on a Fuller type of coordinate system, you're much more likely to think, well, what are the repercussions? If I do this, what does it mean to the rest of the universe? Because I know every action has a reaction and a result. I can't have an action all alone. I can't have an area bounded by three lines and say this is infinite out here. So there's this word, infinite. And what we're doing in geometry is we are defining things. It's a whole series of definitions. And this is a dividing function. It's a matter of taking the whole, which you can't say, what is that? That's not a bubble. A bubble is something I've separated out from the whole. This is something definable. So to the Descartes coordinate system, we would say anything we can't define is infinite. And to Fuller, we say what we can't what you can't define is undefined, which is not the same as saying it's infinite. So to Fuller and to this way of perceiving geometry, the universe is finite, but it cannot be defined. The only thing that can be defined are subsets of the universe. I can define a tetrahedron. I can define a number of things. Okay. So what we want to do is try to get the idea of what the jitterbug is. Tony said we all made a jitterbug, right? You've all seen a jitterbug. You've all seen the basic coordinate, the vector equilibrium. I'll get that out in a minute, but okay. No, this one doesn't erase, Tony. That's not going to do. They're going to take me away. How about this one? All right, I got a good one. I got a hot one. Okay, so now the geometry that goes along with this coordinate system is very old. It goes all the way back to the Greeks, and it's based on a set of assumptions that you can't find in real life. And that is the great problem. If we say, for instance, we have this guy. I say it's a simple question. What's the difference, ignoring color, what's the difference between these two objects? These are obviously clearly definable. Those are both icosahedrons. So what's the difference? Size. Okay, so size is a matter of dimension, right? So we want to get dimensions. This is an attempt to explain size, dimension. So the original assumption, start with a point, no dimension. And in the real world, the so-called real world of everyday, touchable reality, seeable, feelable, depictable by the senses, there is no point without dimension. Every point has dimension. So this assumption is a very strange assumption to base your geometry on. And that is, this is called no dimensions. Okay, now if you line them up, and then you get one dimension, that's a line. And you add all these zeros, and you get... And then, presumably, this has no width. But if we stack a whole bunch of them up like this, then we end up with 2 dimensions. We get a plane, which has no depth. And of course, and is, you know, there are none of those. Every piece of paper has depth. Every plane has some depth. And if we take, so now we're up to 2 dimensions. And if we take all the planes and stack them up, then we add zeros again, and we get depth. Then we have volume. Now we have 3 dimensions. Okay, to Fuller, to synergetic geometry, there's only one dimension, and that's time. And this dimension has this geometry has 3 dimensions, and it doesn't have time. Time is erroneously thought of to be the 4th dimension, which it, to my way of thinking, it is not. So if I say, what's the difference between these two? We say size, or how long did we let them grow? Integrated rate times time. That is dimension. Okay. So how am I going to describe if I get onto Fuller's coordinate system, which is a 60-degree coordinate system instead of a 90-degree coordinate system, which is the orange shape in the middle of this tetrahedron. This is a tetrahedron with each edge divided into 4. There are 12 radiating vectors, each coming out of the middle in a plane. There are 4 planes, 4 hexagonal planes. All of these are unit edge lengths. And they all come out at 60 degrees. Now, if I want to describe something on this coordinate system, I describe it only in degrees, only in angular degrees. And an angle an angle is sub-cycle. It is less than a cycle. Okay, that's an angle. If I'm going to say size, this one's bigger than that one. Now, relative to what? Relative to who? If I'm a little guy, this would be real big. If I'm a big guy, this is real little. Okay, relative to me. Okay, size is relative to something. Relative to what? I got to have some single cycle to measure it against. Otherwise, it's just a description. So there are two distinct phases of geometry. One is describing what I've got, and the other is saying how big, relatively. Now, this angle, I could say this is 30 degrees. Now, there's absolutely no size in there whatsoever. I can say this is a triangle. That has no notion of size. Size doesn't come in until I say, well, I'm going to take this stick this long. I'm going to call it a meter. I'm going to put it in glass. I'm going to freeze it somewhere in a vault so it can't shrink or grow anymore. That's size. And that is size back in France whenever they invented a meter stick. Today, size is based on an atom pulsing and the wavelength that has to do with the particular molecular structure of that atom. And everything is a measure of so many cycles. As the atom pulses, if it goes 50 cycles, that might be a second. It might be 50,000 cycles is a second. Okay. So I don't know. I really don't get the feeling that I'm really getting this across to you. I'm not sure, but it's not really.
Well, when you said the meter was a start from something as a size, it was a start from the measure of the world in the equator. You're now taking it from an abstract, which was dividing it by whatever to get 1 meter down to a known phenomenon, maybe the wavelength, which is no longer an arbitrary.
Right, or it could be a foot. You know, if you're building pyramids, it could be your foot, or it could be the distance from your elbow to the tip of your finger, or it can be a knot, which is a nautical mile is 1 degree of arc of the equator, right? I mean, they're.
To go from a measure of cycles, so the thing is 50 cycles, not 100 cycles, like choosing cycles to measure.
Okay, but the point is that the main point I'm trying to make is that you can describe anything without any reference to size, and dimension is an entirely different animal. Dimension is strictly how long do I let it grow? How long do I let it, once I've described it and I say this is a tetrahedron, I want to be in the middle here looking at it. In order to get into fuller geometry, it's necessary to get into the inside of the structure and view them from the inside. They are defined from the inside in terms of angular measurement. On the Descartes coordinate system, the observer is pushed outside of the painting. It's like a Renaissance painting where you stand outside of it and look at it, and you view the structure from the outside and describe it that way. And it automatically has 3 dimensions, and it automatically does not have time. In a synergetic coordinate system, you describe it from the inside. It only has description. Dimension is a secondary and completely different animal, and there's only 1 dimension, and that is time. How long do I let it grow? Radially. Okay, synergy is also called action-reaction geometry, or it's convergent divergent geometry. The sun is spewing out electron energy, radiation, photons, divergent, omnidirectionally. In order to make structure, that's a good question. How do we make structure? Okay, if we want to make a structure, the Earth itself has the great tensional gravity pulling in. So we can either take our rocks and stack them up and use the tension of Earth itself to hold them there, or I can create artificial gravity in the center and pull everything in toward the center. Okay, that's what we try to do with all of our little structures. If we look at these structures, they are made by pulling in. That's all. There's nothing stacked up. There's no keystone. There's no cornerstone. And the Earth's gravity is not important to this structure. Any of our rectilinear buildings if we have a building like that sitting on the Earth, this huge tensional element of gravity holds all these things in position, sitting on the foundation, until we get a little jolt or something. If there's a quake or some kind, the minute this gets off balance a little bit and starts leaning like that, then the gravity is a total enemy, and it just crashes it down. The geodesic domes and all the geodesic structures are based on creating artificial gravity right in the middle of them and pulling everything in toward the middle until they can't get in any further. That creates volume. That makes structure. This is another one done exactly the same way. And what I'd like you to do is to get your hands on these. I have one here that is released. It doesn't matter how many elements there are. They all want to go away from the very middle of this structure. And if you look at any one of these and feel this for yourself, I'll pass this one around. All the tensional elements do is pull in. All the compression elements do is they want to get out. Now, if you go back to the bubble or the balloon, these tension elements represent the air molecules inside the balloon. They're all trying to get out. In trying to get out, the air molecules are moving very fast, and there's the skin of the balloon. The skin of the balloon is like soft. It's rubber. All it wants to do is go flat. If you put a hole in it, let the air out, it'll go flat. All the little air molecules in the middle that are running into each other, they cancel out. They don't matter. The only ones that keep a balloon round are the ones that are actually hitting the skin. And if you consider if all the air molecules in the balloon hit the skin around the equator in one plane, it would make a record. It would go out flat like a record. And if they all hit in two planes at 90 degrees, it would make a tubular snake. It would come out and twist. It would not make a spherical structure. It's not until you go into three completely separate planes that you get a spherical structure. And what we do in making this structure, as compared to a balloon, is I pair up the air molecules that are hitting and represent them as a strut. If you think of two swimmers getting in the middle of a pool, going feet to feet and pushing off in either direction. That's how you could consider these being two air molecules, each hitting the skin of this balloon, paired up. When I do that, that's a vector. I can describe it. And that's mass in motion. Mass in motion can be described vectorially. Okay, so let's pass this around. Let everybody get a feeling of that. Okay, now I'm sure you saw this in the film, but I want to do this again. I want everybody to get their hands on these things. So Fuller started with the assumption that we have to throw out a geometry based on a point with no dimension. We have to throw out a line with no width. There are no lines with no width. There are no things. Like, what is a noun? You know, what is a thing? And what is a noun? You know, as the language is continually changing, it's continually developing. The process of mind is to differentiate, to continue to break down. First I say it's an atom. An atom is a basic building block. Okay, an atom is a noun, temporarily. Then we say, okay, an atom has protons, and it has electrons, it has a nucleus, it has positrons, it has quarks. So the point is that a noun is just a temporary stage of definition. It's a temporary measure of the inadequacy of our understanding of what's really happening. But all of the energy in the universe is continually in motion. We know that now. We know there are no things. There are only processes. There are only events that are always being transformed. The bubbles are always bursting and bubbles are always forming. So Fuller elected to start with a vector because a vector is a description of mass and motion. If you have energy in motion, you can describe it in vectorial terms. And then we cannot think of an event all by itself because we have to have a reaction and a resultant. We know that. Nothing can move without pushing off of something. I mean, even this floor, the Earth itself, has to have some reaction if I move that way. It's really easy to see if you're in a rowboat or anybody that's been on the water. You get that feeling right away where there's less resistance. The Earth itself is so massive that you can't feel it, you can't notice it. So you have to pair up your action with the reaction and a resultant. There are always three phases. Likewise, you cannot have any line without dimensions, so no two lines can go through each other. I cannot make these two lines pass through each other. They have to have some substance to them. So every triangle is a spiral. It has to be. And if I open up a triangle, and I have a positive and a negative event happening in very close proximity so that they grab each other, the energies somehow come together and tie up, then we have structure. And the minimum structure is, of course, our friend the tetrahedron, and these two, of course, go together to make a tetrahedron. And it's just a matter of having a positive action, reaction, resultant, and a negative, bringing them together, and we get a tet. Now, this has stability in time. It has okay, it doesn't matter how many of these you start with. You can start with 1,000 or you can start with 10. There's no stability to any of these joints until you get down to 3. So triangle is when the magic happens. This is obviously floppy. This is nothing. As soon as I get to the 3, it becomes a very stable, regenerative structure. Structure has self-regenerative stability over time. Why? Because each of these is a lever. And there's a fulcrum at each joint, and at the end of that, I cross it. No way, it's going to move now. Now, if we look at a cube, which conceptually we can think of, but it does not have stability in time. It just definitely doesn't. You have to have triangles. You know, Fuller has said triangle is structure. Structure is triangle. That's it. That's the definition. Because mass is in motion, because energy takes the most efficient route, because flowers and oranges don't grow cubically because eggs aren't cubical, bubbles aren't, nothing in nature wants to go this way. I know when I was in school, we used to have this all the time. You'd have a path like this, sidewalk, right? And then you look in the grass, and here's the real path. Here's where the students go. Because no student running around a campus wants to go around a right angle. So the design scientists would look at this and say, what should I do? I should make my path this way. Where I went to school, I used to put up chains here, so you couldn't go across. Then you had to jump the chain to get across. Anyway. Okay. So then you get to, since that doesn't have stability, we don't want to have much to do with that. We don't want to have much to do with these either anymore. They're getting to be in the way. Then we get to the basic solids, the Platonic solids that were defined several thousand years ago that do have stability. You either have 3 triangles around each hub, which makes this guy, or you have 4 triangles around each hub. These are all equilateral, equal edge triangle. Or you have 5, which makes the Icosa. This has got very little volume, most surface area, very resistant to implosion. This is the way rocks break down on a mountain. You find a lot of rocks on a mountain like this. 3 faces. Always. This is the in-between. It's got a lot of resistance to implosion, but a lot of volume. This has the most volume. Now, when I want to make a tent, which is the object of all this, or when I want to make, you can see I'm not an educator by profession, but when I do want to make a tent, I don't want to start with a tetrahedron, because if I start with a tetrahedron, first thing I know is I'm going to have to use an awful lot of fabric, and I'm going to get very little volume. I want to start with a lot of volume and the least amount of surface area. So we're going to start with this guy. Now, if I get this up to human scale and I want to go in there, these struts are going to get awfully big. And that's when the concept of frequency comes in. Now, how do I describe this structure? This is icosahedron. Okay. That's how I described icosahedron. If I get in the middle of this thing and look at it, each of these, from right here, 63 degrees, 26 minutes, and 6 seconds of arc. Okay? Now, if I get in the middle and look at it, right in here somewhere, and I say, what angle from the center of this if I would take in the middle and sweep out a circle, on that circle I'm going to get one of these edge lengths, this green one, and that white one, and I'm going to come right down through here, and that's the perpendicular bisector of this triangle, and I'm going to get the perpendicular bisector of that triangle. So I know that this is 360 degrees. I know that this is it's also 63 in decimal. That's what it is in decimal. So if I take 180 degrees, which is half of this circle, and I subtract 63, 2606, which I will do right now, I get 116 degrees 33 minutes, 54 seconds. I'm going to divide that by 2. And I'm going to get 58 degrees, 16 minutes, and 57 seconds. Okay, now what that tells me is that this perpendicular bisector is equal to 58 degrees, 16 minutes of arc. The edge is 63 degrees. Now when I'm ready to make, which we're going to do, Tony's going to have all you guys make one of these. Okay, you want me to go through that one more time? Okay. I'm going to go through it again in just a slightly different way. Okay, now, if I want to make this one. This guy is based on the icosahedron, or icosahedron, it's often called. It's also called a two-frequency icosa. You can clearly see now one of the circles I'm talking about. Okay? There's 6 of them. Each one is a complete great circle. Each one is an equator. Now, on this one, every one of these is 1/10 exactly of the circumference. Now, if I were to look at that one, I make another circle. And since I know each of those is 1/10 of the circumference, I know it's 36 degrees. Okay, now I can tell you that the entire description of this is 36 degrees of arc. Okay, that's it. Now, hopefully this will get a little clearer as we go. Okay, here's another good example. This is also this one, exactly. This one, however, is put together slightly differently, because in each of the great circles now, for instance, look at that yellow line. There are clearly 5 of these struts. Or if you look at the orange or the blue line, whatever, okay? So, each of those struts, I know, is going 1/5 of the way around the circumference. It's 1/5 of the equator. There are exactly 5 of them. They make a whole circle. It's got to be 72 degrees of arc. I mean, I know that pole is sitting right there, and that's 72 degrees. This is exactly the same. It's just bigger. We let it grow a little longer. Okay, now, on this one, I have the harness is different. The actual tension members that put it together are different. The tension member happens to be exactly half of the strut length. So I know it's 36 degrees of arc, and that's what we based it all on was this one. 36 degrees. So that if we look at this guy, and we look at this guy, get up here where they can see you, please. Okay. If I wanted to put this yellow strut into here, it's going to go right there. And these triangles then would become this tension harness. Okay, now, this is the same one. This is exactly the same one. There's only one measurement in this whole thing. There's only one dimension, and that's this, and that's 36 degrees of arc. That's my description. Now, how long did I let that grow? I let it grow at a rate such that the radius became 1 meter. Okay, now, if I can So we've tried to say, forget about three-dimensional world. There is no three-dimensional world. I assure you that. There's a one-dimensional world, and it is time. I've got energy. We've got energy moving. We know that. E equals mc squared. It's all energy. We got energy likes to tie up different ways. We like to have oxygen, we got hydrogen, we got all kinds of different, 92 of them that naturally occur, and they love to be together. They're regenerative. Aluminum, copper, there's a whole bunch of them. Now, if we try to think of mass in motion as a vector, then I can talk about something. I can represent a vector by a stick. This represents a vector. Now, if I can put these together and describe them from the middle, I'm on my new coordinate system. I'm thinking radially. I'm thinking convergent, divergent. I'm starting in the middle and making bubbles. I'm not stacking things up and letting the Earth's gravity hold them in place, like the Leaning Tower of Pisa. If I let it lean a little bit, I got a real problem. I'm pulling them in to position. Now, from this one to geodesic dome, the only difference is that we learned the original geodesic domes, some of the early ones, they had all tension members all over them, pulling them together. Then they learned that the actual metal itself, or the strut material, you could use the tension in the strut material. You didn't need this harness. This harness becomes redundant. So that when I go to one like this, which is a 2-frequency Icosa, I don't need the tension because just the suction inside of these hubs is doing the tension. Every hub has got to have tensile requirements. It has to be able to pull them in. When this breaks, when I let this break, what happens is they pull out of the hubs. Okay? These are not stacked up. They're pulled in. And that's the main thing I'm trying to get across. That is how we make these tents that I make, or the ball that we're all going to make in the next week. Now, I think it's time to say what is frequency. Because now I have these three here. I have this guy. You see these small hubs too, there's so little surface area they don't work nearly as well. In a larger size, they're much better. In any case. Now I ask you another simple question. What's the difference between these three? Absolutely. Absolutely. Frequency. Okay. Now this is a icosahedron, 1 frequency. Icosahedron, 2 frequency. Icosahedron, 4 frequency. Now, that's why I didn't want to erase this. Now here's another thing. This is so we say, what is this when we power a number? If we're going to make a number go to a power. This is commonly referred to 2 to the 2nd power. It's called 2 squared. Because if you are thinking in terms of right angles, and I do that and take each edge and divide it 2, sure enough, I get 4. And if I want to divide each into 3, to the 2nd equals 9. Point is, it's a misconcept to say this is squared, as it's equally a misconcept to think that a point has no dimension. Because if I look here and I take a triangle and divide each edge into 2, I get 4 triangles. And I can equally well say 2 triangled equals 4. And if I want to, I can divide each edge into 3 and say 3 triangled equals 9. So this should definitely have a suffix, and it should definitely say 2 to the 2nd power, 3 to the... And the same thing with the 3rd power. 2 to the 3rd power equals 8. This is not 2 cubed. It's 2 to the 3rd power. Excuse me, I digress. It has nothing to do with what we're talking about. pretty much. In any case. Here we are. We're supposed to be talking about this. Okay, now. This is a one-frequency triangle right here. This is a two-frequency triangle because each edge now has two divisions. I've taken the middle. Now that's this ball here. Now this whole edge we know is 63 degrees, 26 minutes, and 6 seconds of arc. If I view it from the middle. This line right here, I don't have my map, do I? If I follow that line around and I split this in half and I keep going, I come all the way back around, I will have crossed through 10 triangles equally. And I will have split the circumference into 10. And this is 36 degrees. It's 1/10. It's exactly 1/10 of the circumference. Okay, if I go to, let's just go to 4 frequency.
Let's just recap on that. So to make this one frequency triangle, the icosahedron is a two-frequency structure. We divide each into two pieces. We make it 3 frequencies divided into 3.
When you make it 2, what are the angles?
Well, when you're making it 2, what you're doing there, and if you draw a circle right through there, right through all over, divide each of these triangles equally. The Bruce is saying there are 10 triangles there. So the circle divided into 10, 360 degrees gives you. So the dimension, well, what you say, the size of this is 36.
Are there 5 triangles? 5 triangles around.
5 triangles around each point. Yeah, there's a pentagon around each point. And when you go through across there, yeah, because you're putting one there, one there, one there, one there, and then you go through. 20 triangles in this whole structure.
Okay, when we're talking about one structure,
Yeah.
so how many triangles is
When you're putting it into that 2 frequencies, how many?
Okay.
That only goes through 10.
Okay, in a one frequency, the difference between a structure such as this, where you have your struts, I don't know, do we know about chords? We probably don't know about chords of circles, do we? Boy, these are a disaster. I should have painted these. They get a little thicker if you paint them. It works better. In any case, let me give you the chord thing of the circle, then that's what we need to know right now. Yeah, use that guy. He's much better.
This one here, if you look at these purple lines, they're the faces of the icosahedron. See that now? This is 2 frequency structure. Just read the purple, forget the reds. You've got an icosahedron. You divide it into 2 frequency, and then you're getting the other division. And each one of these is 36, because you can see how this is going right round. The circle's going right round.
circumference, how many pieces are there around the circumference of that? Are there 10?
10 of
Okay.
those, yeah.
So then around the circumference of an icosahedron are 5.
No,
No.
there aren't, because
You don't actually go around.
I just tried to show you that a second ago. On icosahedron, the great circle does not go, it's not complete, okay? If I start here, now look, what happens? I immediately come to nothing,
You're trying
a
to go
perpendicular bisector of a triangle.
and the circle would be here.
And that's why we have here, now I can make that. I can definitely make that if I use a complete circle. Now, let me show you here for a second. On this one, if we have a circle, and I make a chord of the circle, the diameter is the greatest chord I could possibly make. A chord cuts the circle off. The ratio here is circumference equals 2 times the radius. Okay, this is half the circumference, so we take the 2 out. This is equal to pi times this diameter. Is that understood? Pi times the radius, excuse me. The whole entire circumference is equal to pi times diameter. This is the diameter. This is half the circumference. So that ratio is pi divided by I'm going to get there. I'm trying to get to the board right at the moment. I have so many objects in the way I can't get there. Okay, circumference is equal to 2 pi times the radius. This is equal to, well, let's use diameter. Then I won't get confused. Okay, it's diameter times pi. This is half of this arc. This diameter cuts the circle into 2 arcs, each of which is equal to half the circumference, which is equal to half of this. The ratio of this line, this circumference, to this line is therefore its diameter 2 wait a minute. It's half of pi. It's pi over 2, which is equal to 1.57. Okay. This green line from here to here is the equivalent of diameter times pi over 2. This line is equal to the diameter. So it's pi, the ratio is pi over 2, 1.57 to 1. This arc is 1.57 times the diameter. The entire arc is pi times the diameter. Okay, now, as I make this, that's the greatest ratio I can possibly have, is 1.57 to 1. As I cut my cord shorter and shorter, as I cut a cord like this, the ratio approaches 1 to 1. Pretty soon, if I make a cord out here so short, I'm cutting off so little of the arc, the ratio, as a limit, approaches 1. The whole concept of frequency is to approach 1 with the ratio of the arc to the cord. Because as I do, I get more and more volume. I include more and more of the sphere. So in this structure, a great circle only passes through the perpendicular bisector of 2 triangles, and it is the edge length of 2 in each hemisphere. It's the perpendicular bisector of 4, and it's the edge length of 2. Now, however, if I take and run the great circle this way, it goes through the midpoint of 10 triangles as it goes around, which you can clearly see as these red lines. These red lines are complete. They are each a great circle, and they each have 10 divisions. The purple lines are the main triangles. They're these triangles. And each red line is going right through the middle of each triangle edge, making a great circle, dividing it into tenths. Okay, now, you see, this is at the stage where the chord, at the Icosa stage, the chord is like this big. See, we're lopping off a huge amount of the sphere. We're lopping off all of this part of the sphere by dropping this chord in here. When I go to 2 frequency, instead of having this triangle be flat, I bring this out to the surface, this to the surface, and this. The ends of every chord are on the surface of the sphere, or the circle. You see how the ends of the chord are on the surface. Now, if I just go ahead and make it spherical, if I just go ahead and make it round like this one, there are no more chords. This is simply 1/10 of the circumference, that's all. I'm not cutting anything off. There are no chords. Boy, I hope, did that get through? Did people get that or not? I don't know if I'm really coming across here. All right, now, look at these. Just look at these for a second.
Imagine these solids being inside.
God, these sons of bitches will not stay together.
If you take the sphere around each point, imagine this being a circle going around here. Hold on a moment. This circle here is not going to touch this point. It's going to go around this point. Now, a great circle is a circle that's equivalent, that would go across the diameter, halfway across the circle, to that diameter. That's what you call a great circle. You have lesser circles if you cut off the sphere at other points. But what's important is the great circle. So what you're seeing there is a great circle going around on the icosahedron. Then Bruce is saying these lie on the great circle lines, these red ones. But what you've got is the great circle going along here. Then you've got another great circle going along here, and then you've got another one here, and so on. So you've actually got this. If you look at this here, the red lines in here are taking exactly the same formation as this, which is exactly the same as that.
Okay, now, okay, get this guy out of the way. These 3 right here show you how rapidly you approach a sphere. Now, see, one of the concepts of earlier geometry is that a sphere is a continuous surface. Also, a circle is a continuous line. Physics has not found anything continuous. There are no continuums. There are quantum leaps. Everything happens. I mean, one either does think or one doesn't. There's no such thing as sort of thinking. You either go to one level of energy or you jump to the next if you're an electron. They're quantum leaps. There's no in between. Now, if we've only gone from one frequency, which is clearly very angular and low volume, to 2 frequency, which becomes very spherical very fast, and only 4 frequency, right here. At 16 frequency, it's impossible to distinguish that it's not a continuous sphere. The eye can't tell the difference. Because this, right now, you see, now we have a chord here that's way out here like this. We're approaching a 1-to-1 ratio very fast. Now, this one right here is this one. This is the ball we're going to put together. As soon as I finish talking here, we're going to put this big one together.
And everybody see, Bruce is using the same color system here. So the purple on this, and the purple on this is the icosahedron. So that drawing up there, that triangle is 1, 2, 3, 4. Then it becomes to one of the pentagon points, one of the points where 5 members come together, which is the original point of the icosahedron. You'll get to see this as you get used to this.
Can you see that now?
So you can pick out these points. There's one there.
The red lines are the same red lines. These still fall at the midpoint of this main triangle edge. There's always the main triangle. And the dodge symbol is always the giveaway. If you find this star, the 5-ness, 1, 2, 3, 4, 1, 2, 3, 4. Okay, I'll give you those just a second. I'm just about ready to do that. Just ready for that. Okay, no matter, this takes, there are 12 hubs to make icosahedron. It takes 12 positions, and there are 30 relationships between the positions. It doesn't matter how high the frequency goes, there'll never be more than 12 pentagons. The pentagon is called the Icosa cap. And if you have a 6 frequency or a 16 frequency, you're always going to have 12 and only 12 pentagons. And the number of hexagons goes up very rapidly. Okay, so if we want to divide this one, there are several ways to do it. You can pick different ways using spherical trig of dividing up the triangle. What I'm going to show you, the particular degrees I'm going to show you are the ones that I use to make this ball we're going to put together within a half hour or so. We're going to start on it. And they're not the only ones. There are other ways to do it. You could divide each edge length equally. It just so happens that in this one, we divide them up this way. This is 14 degrees, 23 minutes. Make that 32 minutes and 43 seconds. This is 17 degrees, 10 minutes, and 18 seconds. Now, this repeats. It's then the same thing, 17, 10. Okay, how come I don't divide it equally? Let me put the rest of them in. This guy going across here is 16 degrees, 58 minutes, 41 seconds. This guy in here is 18 degrees, 41, 58.
Does everybody get this also works? So these are all to do with from the center. So Bruce says you must consider yourself to be in the center of the structure looking out. So this is the degree from the center point. But you usually write it on the drawing. You usually write it on the actual outside of the dome. This is just another way of writing it, really. This is how you must think about it.
Now, why didn't we choose? We could have chosen, for instance, we know this whole edge length is 63, 2606. We know that half of that is 31 degrees, 4303. I could have picked half of that, which would have been roughly 15 degrees something. (15 degrees, 51 minutes, 31 seconds. And in fact, if you want to look at this sphere real close, you'll find that 6 of these pentagons are framed with white, and those 6 represent an equal edge division. In other words, one hemisphere of this is done one way, and the other hemisphere is done the other way. You can do that to get these equal. Now, I chose to do it the other way because these triangles here, if I split the edge up this way, these become equilateral triangles. There's an A and a B. But not only is this edge 16, 58, 41, but so is this one, and so is this one. Not only is this 18, 48, 50, whatever, but so are all 3 of them. Now, when we put this big ball together, you'll see why I've colored it this way. The reason I've done it this way is this. Pardon me for a minute, but I have to draw it in again. Okay. This is going to become a pentagon right here. And now look at this ball and look at this ball. This has all the information in it, and it has all the struts. When I go to making the ball we're going to make, that this class is going to make, we're not going to put in all the struts. Just as here, I've chosen to leave out all of these purple ones. Okay, so that the pentagon shows up as a void. So, like I say, on this, the only measurement really is the one triangle. Okay, now on the ball we're going to put together real quick, also we leave out this. The pentagon is one piece of fabric. We don't put those struts in. This becomes a hexagon. Nothing goes there either. This becomes a hexagon. This is a hexagon. This is another pentagon. In other words, the only thing we really need to know is how big are these triangles? Because this triangle edge is a pentagon edge. This triangle edge is a hexagon edge. That triangle edge is a hexagon edge. In other words, if I know this edge, it's got to fit there. So what I want to do is I want to have my triangles equilateral. It's much easier for production. Now, see, now you get down to what are we going to do? Well, making these models is one thing, you know. I can work all my life and make these models, but if I'm going to go into mass production, here's another Fullerism that I like to throw out. Ideas are easy. Inventions are hard. And mass producing the invention is the hardest of all. And it's really true. If I could tell you the number of times in a design room at North Face that a very well-meaning and well-intentioned and bright person has come in there and said, why didn't you do it this way? I got a great idea. Why don't you make your backpack or your tent or whatever this way? And you go, that is a good idea. I tell you, that's a good idea. Now, all you got to do is go start your factory and make them. The reason we don't do it that way, who knows? Maybe it has something to do with the way the sewing machine works. Maybe it has something to do with the way we have to cut fabric. Maybe it has to do with the way the fabric comes to us. Maybe it has to do with the fact that if we did it that way, we never sell any of them. We go out of business. So the design effort then becomes a matter of simplifying. So I choose to break it. This is a simple way to break it down. I make every edge length a fourth of the big edge length. But then it turns out these triangles are not equilateral. Okay? I don't want that to happen. Now, unfortunately, on the sixth frequency, the one that we're going to design together and make, which I have diagrammed here, we're going to have to consider these triangles. This is a pentagon, this is a pentagon, this is a pentagon. We're still only going to have 12 triangles. Okay. 12 pentagons, excuse me. This guy has 12 pentagons. 2 frequency. The 4th frequency we're going to put together is going to have 12 pentagons. The 6th frequency is going to have 12 pentagons. Now we're going to have an A and a B triangle also. Unfortunately, they're not equilateral. I don't know how to do it to make them equilateral. This hexagon is an equilateral hexagon. It's a regular hexagon. These 2 hexagons right here, which appear on this edge too, and on this edge too, are not equilateral hexagons. They're not regular hexagons. So we just have to, that's the only way we can do it. That's the way we're going to do it. The information for that one, well, I don't know. I'm not even going to give you that today because it's not important. We'll get to it later. There's not much more information. The angles get smaller. You see, as I split it up, the more I split it up, the smaller the angles get. So I don't even have this in order. This just happened to be my notebook, so I'm trying to find my... Okay, it's not even in that notebook. Okay.
One thing might help. And, I think people probably got the idea of this one was this, with these taken out. The one we're now going to put together is a much larger one than this. It's 4 frequencies, isn't it, Bruce?
Yes.
So let's just do it out. This is the 4 frequency one. So we'll first of all take these out. So this is what Bruce has done on this drawing here. You take these out and make them flat. You put them out in 150 material. Take them out. So you'll get to see what you make probably better. And we'll leave these triangles in here. Which ones do we leave in, Bruce? Do we take that one out?
You're opening up a can of worms here, buddy, I'll tell you that. We could be here for the next 3 hours. Yeah, it'll lose its stability.
Yeah.
It won't have stability without the fabric, incidentally.
But you can start getting to see what...
If...
Are you starting to see what's happening there?
No. I assure you don't.
It's treating these as flat planes.
Okay, there's one more big concept I want to get across before we go ahead and put the ball together. It's 3 o'clock now. How are we doing? Should we go ahead and get this? I think maybe I'll be done in 10 minutes. Then we'll take a break and put the ball together. Okay, Tony? Sound good? Okay. Yeah, we'll have questions to anybody with questions. But the idea now is, how do we get from angles? Angles are nice. We can describe it. We know we can describe it in terms of angles now. How do we figure out how long to make that stick? Okay, so suppose I decide I want to make a 2-frequency model tonight. I want to go home and make one of these. Okay, the guys told me that this edge right here is 31 degrees, 43 minutes, and 3 seconds. This edge is 36 degrees. That's all I got to know. There are only 2 lengths. There's only an A and a B. Okay, now the question is, how big? Now it's time for dimension. We suddenly enter the real world. You know, why did I say we enter the real world? Okay, I have a concept in my mind. I have an idea. My idea is tetrahedron. Okay, now I can perceive of a perfect tetrahedron. Absolutely perfect. Can I make a perfect tetrahedron? No way. Is this a perfect tetrahedron? Impossible. I have degree of error here. Between my concept, which is purely metaphysical, it is not depictable by the senses. It's like a dimension, like a line with no dimension, of tetrahedron, and my actual tetrahedron. I have my precision of measurement. How accurately can I measure my sticks? Then I have my tools. Once I've measured, how accurately can I cut it? If I'm going to cut it on a bandsaw, you know, I could easily be off by 2 millimeters on each one of these. On a base of maybe 50, 60, whatever that is, 70 millimeters, I don't know. It could easily be 3% error. Okay, now I got my materials. The materials themselves, look what I'm working with here. I got a little screw and a nut, and I got some plastic tubing. So once I'm ready to get out of the concept stage and go into actually making something, that's the only time dimension is time to come in for. Now it's time for dimension. This is time. It's the only thing. It is. We're going to make one in the real world. It has to have time. So, okay, that's where we come into our formula for chord factor. It's a factor, chord factor, equals 2 times the sine of the central angle divided by 2, or half the central angle. These are central angles. These are described from the middle. I'm in there looking at it, and I'm saying that's 36 degrees of arc. It's 36 degrees of arc if the thing is the Earth or if it's this big. So the only question is, how big is my radius? Radius is the time factor. How long do I let it grow? Centrally from the middle. How long do I let it expand? before I say, okay, that's it. So I take the central angle, which in this case is 36 degrees. We'll do this one. I divide it by 2. Sine of 18 degrees times 2 is the factor. This is the time when the modern geometer needs more than dividers. You've got to have a way of doing trig. Now, you can use trig tables, but any one of these machines now for about, I don't know, Christ, it's $50 or $60 at the most, maybe even $30. You can do all your trig. So I need to be able to take 18 degrees and get the sine of it, and that's very simple. I hit this button. I multiply that by 2. I fix it out where I can display it, and this happens to be 0.6180. Okay, that is called my chord factor. So that's for my 36 degrees. Now I'll do the 31 degrees. I'll take 31 degrees, 43 minutes, and 3 seconds. I'll divide that by 2. I'll take the sine of that and multiply that by 2 and display it so I can see a little more of it. And that one is chord factor of 31 degrees, 43 minutes, and 3 seconds equals 0.5465. Okay, now the only thing left to do is put in the dimension. This radius is 30 centimeters, 300 millimeters. So I take my radius equals 30 centimeters times 0.5465. That equals this strut length. That is the purple strut length in this case. .4, and I'm in centimeters. The other one is 18.54. Okay, those are my only 2 measurements. That's all I need to know to make this ball. So anybody here should be able to make one of these pretty easy. Just pick your radius. Of course, I will eventually have to allow for my hub. The hub will take up some room. The hub does not have no dimension. It does have dimension. However I connect them, I have to do it. Now, if, on the other hand, I'm not using the chords and I just go ahead and use the great circles, that's how we make this one. We take the actual circumference itself and use it as a circle. I don't make any cutoff of it at all. Now, in that case, I don't use chord factors. I use percents of circumference. Okay, this is going to go. Okay, so in order to make the easiest one, the 6 strut one, I know that I'm taking the circumference and dividing it into tenths, which is 36 degrees. So now I pick my radius. I say, okay, I want a radius equal 30 centimeters. Circumference equals 2 pi r. So I get my circumference. 188.5 centimeters. Okay, so I want each of these divisions to be 1/10 of that. That's pretty easy. In other words, I would put a hole, or I would put a fix. Okay, yeah, this is a lot easier to see. 6 of these makes that. And that's all. And all I do is I take this and divide it into tenths. So I say this strip is equal to 360 degrees of arc. This is equal to 36 degrees of arc. Now, if I want to, I can also take the question arises is how do we get these? We get these by spinning these. I take this Boy, that one is just a disaster. If I take this and spin it, I'm going to generate a great circle. If I were to take a time-lapse photography or whatever and put a light on the midpoint of this edge right here, these 10 edges, it would sweep out this circle. Because I have an axis of spin set up by the two opposite vertexes, and I spin them. There are 12 vertexes, therefore I can have 6 different axes of spin. So I can have 6 of these. Now, were I could also make an axis of spin by putting an axis through the opposite edges of this. And this guy's a little big for this, but I could, if I had an axis through the opposite edges, you see that'll spin too. And that will describe 15 great circles. There are 30 edges. There are 15 possible choices I could make. I could also put my axis to spin right through the middle of a face, and opposite faces, and I can spin it this way. And there are 20 faces, and that will make 10 great circles. The 10 great circles that I make, it just so happens, cross diagonally across these pentagons. And it makes a great circle. And each one goes from this point to this point, which is equal to, and it does that 6 times. And that is equal to 60 degrees of arc, which is 1/6 of the circumference. And the chord factor for 60 degrees is 1. Just so happens. That's unit radius. This ball here is made up of 16 strips. It has a 6 like this, with each one being 1/10, plus it has 10 with each measurement being a 1/6, and that makes this star with inside the pentagon. I can also add the 15 from spinning this way, and that would make the perpendicular bisectors of each of these triangles. So there are 31 great circles that you can generate by spinning icosahedron. If I take these out and get down to our, if I get down to the vector equilibrium, and if I spin it, let me just get down to this guy here for the heck of it. I can generate 25 great circles from the vector equilibrium. And it just so happens that with those great circles, you can describe any geodesic dome, period. All the information you need will be there. You see, now we can spin this, and the reason we spin these, the reason we can do this is because if a bubble is floating free, if any structure is free, and it's not restricted, it will spin. They all want to spin. They all will have a neutral axis to spin. Okay, if I spin this one, the same thing is going to happen. A point on the mid-edge of this is going to generate a great circle. I can spin it by going through the opposite faces. I can go through the edges. I can go through the vertexes and spin it. And when we do that, we get another ball, which is over here. And this is based on spinning the vector equilibrium. And I don't have all 25 in here. I only have 7 of them. In any case, I have all, if anybody wants any of that information, yeah, this is a big jitterbug. This is a nice jitterbug in that I have it 2 colors. And you can clearly see that as it lines up, you do get 2, one color, you get double vectors at each one. And when we go through and make the tet, we get 2 green ones, 2 green and 2 white at each one. And this is because the vector equilibrium is the closest packing of 12 spheres around a central sphere. And when you swallow up, if the central sphere isn't there, it goes into, that is the icosahedron. 12 spheres closest packed around a void is the icosahedron. If each of those 12 swallows its neighbors, Okay, which is to say, in this form right here, you would have a central sphere, and each of these 12 hubs would represent the center of a sphere packed around that central sphere. If the central sphere gets swallowed up, it contracts slightly to the icosahedron stage, which is where we started with this guy. And then if each of those 12 sort of swallows up its neighbor, if they sort of double up, you get down to the sixth, which is this is the closest packing of 6 spheres around a void, and you get double vectors on every edge length. And if each of those swallows up his neighbors and whatever, I don't know exactly how all this works, I can tell you, but I know just a little bit of it. Then you end up with the 4 vectors along each edge and the tet. And anyway, the point is that Tony's going to want to have all of us make one of these tonight, just so you each get the feeling of this, how magical it is that these strips can just go together and make a ball like that. And I have the information, I have all the recipes if you want to make the vector equilibrium or all 31 of these. And when you do make the 31, you can really see that the great circle on the icosa goes edge length, perpendicular bisector, perpendicular bisector. And that's how you split it up. You know, instead of dividing it into tenths, the first division is 63, 2606 divided by 360 is 18, so it would be 18% of whatever the circumference was. And in fact, when we make the ball, both factors are involved. First, we have to make the skin with the chord factors. But then the poles themselves are a complete circle. So when we make the poles, we use the circumference method of percentages of circumference. If the edge length is 18 degrees, that's 1/20th of circumference. So I know that's 1/20th, that pole length is 1/20th. Okay, that's all I have to say. I'm ready for questions. Any questions? I'll show you one more nice one. I have one real nice one here. This is also vector equilibrium. And this is tensegrity vector equilibrium. We still have our 8 tetrahedrons going to the middle and 6 half octahedrons. That is what vector equilibrium is. And you can make it this way by having 4 circles of 3. And I have that recipe if anybody wants that one. And this is the other nice part, is that when you get into this coordinate system, you see the hierarchy of structure. In the middle, these white lines describe octahedron. You can see that if you look close. And if you connect the midpoints of octahedron, you get vector equilibrium inside. And the midpoints of the big green tetrahedron make the octahedron. So in the middle of every tetrahedron, there's an octahedron. In the middle of every octahedron, there's vector equilibrium. And it's made up of tetrahedrons and half octahedrons. And this you can fill all space this way. This is how you make your octet truss and everything else. So that's it. Now we should put the ball together and have some practical, real life.
It's just that people want to go. First of all, we're going to put this big ball together, which is this one. What we build, what we image in this is that's an outline. When we've done that, we want everybody to make one of these. We've got all the charts. The introduction, rather than that's still everyone. So, and tonight, or before Friday, we managed to actually make another structure, 2 frequency structure of this sort, or a flat plate one. But we'll come back to that later on. And then you'll really be able to write up the plate and look at these structures. And on Friday, we're going to look closer at tensegrity structures, so you can get into some of those over the weekend. We're going to talk big tensegrity structures. So we'll just move. So I think to build the big one, we probably need to move all the chairs out and get the big space. Push the projector back. Let's go.
Welcome. I hope you got the idea. The math you have to dig out. The idea is to get
several motions.
As far as the, okay,
Yeah.
Is it questions now or what?
We'll leave the questions for the moment.
Big, beautiful piece of mahogany, cost $500–600, got file drawers on each side. Chair is absolutely beautiful. I could sit here, it's like those bucket seats in a car. It's just extremely comfortable. But what I want to talk to you about, sit down, fellas. And ladies, sit down. Now, what I wanted to talk to you about is, and I've been accused of being an Archie Bunker, and that I'm not flexible, and that probably is true. I'm going to discuss with you a couple of things. One of them is failure in the life insurance business, and that's a beautiful damn subject to start out with some brand new agents. Failure in the life insurance business is brought about by many things, but perhaps the number one item that causes failure in the life insurance business, or the number one item, I'm sure, is lack of sales activity. Now, it isn't knowledge. It isn't whether or not you're good looking. It isn't whether or not you smoke an old crummy pipe. It isn't whether or not your shoes are shined. It isn't whether or not you went to the right college, you belong to the right clubs. It isn't whether or not your dad was a great big man in the community and belonged to the right country club. It isn't whether you got an MBA or you dropped out the 8th grade. It doesn't have a damn thing to do with your success in the life insurance business. The number one item in the life insurance business is that causes failure is lack of sales activity. Now, that brings me to my prop that I had here. The prop is this damn desk. One of the number one causes for people not having enough sales activity is that they are very comfortably ensconced behind a beautiful big wooden desk. I'm sure all of you have been provided desks, and I'm sure all of you would feel very, very bad if you didn't have a nice desk and a nice chair and a nice office. And hopefully you aren't in a bullpen where there's five desks in one room. But let me make a couple of points. Number one, in a business where the work comes to you, an underwriter at the home office, an accountant, an attorney, a person in a travel agency, people who work, a banker, where the paperwork flows to them, a desk is of some importance and it should be halfway comfortable. The son of a gun spends about half his damn life behind it. In a business like ours, where with new agents, nothing comes to you. Hell, you wouldn't get 3-4 pieces of mail your first month in the business. The desk is of zero importance. You are working in this business when you are looking for, talking to, or trying to sell a product or a prospect. Now, new agents don't have prospects coming up and knocking on the door and coming in and saying, I want to buy from you. It just doesn't happen. But there's a psychological thing with the desk. The psychological thing is that it's the damnedest crutch that we ever had. You see, I was born pretty close to 60 years ago and in a town that had no hospital, so I was born at home. And I'm sure I was a suckling baby. I don't think they even had bottles when I was a baby. I don't know, maybe they did. And then I got to where I was rubbing the edge of the satin blanket with the thumb in the mouth, just like I've seen my kids do. I did that. Then I got onto, let's see, another pacifier, I guess, was a yo-yo. That was a damn good one. Then I think maybe Lucky Strike cigarettes, about 12, 13 years of age. And then at 16, you could drink beer then. I think it was in 32. So beer was a nice pacifier. And then I went to college, and it was still beer and more cigarettes, and went in the service, and I had a dandy pacifier there. I got to where I was handling those martinis and doing a pretty good job of it. And all of my life had been regimented just like most of you. You are either just out of college, or you have been in a 9 to 5 or an 8 to 4 job. You have not been in an activity or a job where you had to get out and make something happen. Almost everybody that comes into this business has been in a capacity before they came to the business where the work flowed to them. Now, that's reaction. Ours is a business of action. Man, you got to get out and do something about it. Consequently, you get out of the service where it was absolutely regimented. Like the old Army thing, you know, keep your mouth shut and your bowels open and never volunteer. Well, you know, just couldn't do any thinking for yourself. In college, your classes were scheduled, your study was scheduled, your meal times were scheduled, the whole thing was scheduled. Now, you're out of this type of atmosphere, and you come into the life insurance business. And the first thing that we do is give you a great big desk. The desk is nothing but a pacifier. It's something to hide behind. It's a crutch. You are not working when you are in the car on the way to the office. You are not working when you walk through the office and bat the breeze with 2 or 3 guys. You are not working when you are sitting behind your desk. In fact, in our agency, the most depressing thing that can happen to me is to come in and find everybody at their desk. Now, oddly enough, there are people that think they're working when they're behind their desk. I've known general agents that have swivel chairs themselves right out of the damn business. Because a general agent's job is recruiting, motivating, training, and supervising. And there's hardly any recruiting happens at the desk, no training, no supervising. But you get terribly comfortable. Boy, it is comfortable. Now, in this business, where you are only working when you are looking for, talking to, or trying to sell a product, and you're new in the business. I mean, you've been here 2 weeks, and anybody going to come in and say, I want to sit down with you. I want to talk to you about life insurance. There's not a damn soul going to do that. Now, if you think they are, somebody hadn't explained things to you very good. You see, if I had my way, except the home office, I'm sure wouldn't let me scrap all of the furniture that we have. If I had my way, we would scrap for all new agents, we'd scrap all the desks, all the chairs, and we would have a little room that would have a chair, a side table, a telephone, and a pad of paper. And you'd make a few phone calls, you'd receive a few phone calls. You wouldn't need a basket to hold your mail because you aren't going to have any damn mail. Now, but you've made your 4 phone calls, and you've opened your 2 pieces of mail, but you don't have any desk to hide behind. You see, now you're sitting there, and all of a sudden you begin to feel squirrely. Geez, what'll I do? This doesn't look good. And you get so nervous that you get up and do something about it. And doing something about it is going out and making a call, or seeing if you can find somebody that you can talk to about our product. I sound terribly serious on this, but I can assure you I have seen agents 25, 30 hour a week themselves out of the business sitting behind their desk. And no new agent, in my opinion, no new agent should put in 12 hours a week in the office. Now that's a little over 2 hours a day, and it sure doesn't take a great big slab of mahogany and a great big beautiful swivel chair to accomplish 2.5 hours a day in the office. You see, it's a status symbol. The desk is a status symbol. If you didn't have one, you'd be hurt. You'd be mortified. You probably wouldn't have come to work for us if we hadn't have said, we'll give you a real nice desk. I know it's a status symbol in the home office. I think it's the second vice presidents get a wood desk, and maybe a wood chair or something, and the second vice presidents or the assistant vice presidents, however it works, get a metal desk, and I don't know whether they get a wood chair or not. It's just all dingy. In other words, it doesn't have a damn thing to do with a person's effectiveness on the job. So if there's any one thing that I can tell you, and it sounds so trite and so stupid, but I can assure you the desk is a crutch. How I know is I've been through the same thing. I've hid behind the desk many times when I didn't want to go out and make a call. Call reluctance is a very, very huge retardant to making sales. And you can ease your call reluctance just to beat the damn band if you are extremely comfortable sitting behind a desk. You could even go home, you can rationalize it so much that you go home at 5, 6 o'clock in the evening and tell your wife that you're absolutely, totally beat. Or you gals can tell your husband that you're absolutely, totally beat. I had an ungodly, horrible day. And you had an ungodly, horrible day because you were sitting on your can in a very comfortable chair, hiding behind your desk, because then you didn't have to go out and see anyone and possibly have them tell you no. You see? It's a very, very wonderful way of hiding. And I guess in my 20-some years of recruiting and hiring and working with agents, I honestly, I really sincerely believe that maybe 1 out of every 4 or 5 that went down the tube, and we've had lots go down the tube. I'm not, I'm not so good that we haven't had failures. I think 1 out of every 4 or 5 went down the tube because he thought he had a 9-to-5 office job at a hell of a nice plush office with a hell of a nice plush desk and papers stacked all over. Nothing constructive happening. It's all out there. It is all out where the people are. It isn't in here.